Welcome back everyone, Patrick here, moving on to another word problem dealing with exponents. So we're told that 1/4 of a certain drug is used every hour it is in a patient's bloodstream, and then we're told 200 milligrams is given as a dose, so that's the initial amount. And then two questions here. So part A, we have to find an equation for the amount of the drug in the bloodstream after every hour. And then in part B, we have to find out approximately how long will it take for the amount to be less than 10% of its original mass. So even though this is another word problem dealing with exponents, notice that the wording in this one is kind of unique. We haven't done a question like this with this kind of wording, but the equation and the process is still going to be the same. So as I've done in previous problems, what I like to first do is create a table of values that we can look at, and then just to, number one, make sense of the problem, and then we could use that table of values to create an equation and then also to check our equation. So here we'll have hours, and then over here we'll have mass. So what we're told is that initially a patient takes 200 milligrams of a certain drug. So at time 0, the initial mass is 200. And here's where you got to read it carefully. So we're told 1/4 is used every hour it is in a patient's bloodstream. So after 1 hour, 1/4 of this dose is used. So if we start off with 200, well, what's 1/4 of 200? That is 50 milligrams. So that means 50 milligrams is used. So what's the mass going to be after 1 hour? Well, it's going to be the initial mass, 200, minus the amount that is used. And so 150 milligrams would be remaining after 1 hour. All right, starts at 200. 1/4 of it is used in the bloodstream. And so 1/4 of 200 is 50. So after 1 hour, 150 milligrams is left. What about after 2 hours? Well, then what's going to happen is 1/4 of the 150 is going to be used. So let's actually just do it here. So what's 1/4 of 150? Well, that's going to be 37.5 milligrams. So 37.5 milligrams is going to be used. So the amount remaining is going to be 150 minus the 37.5 milligrams that's used to give us, what would that be? 112.5 milligrams. And then you just keep repeating that pattern. So then 1/4 of this is going to be used, and you subtract that amount from this amount to get the amount that's going to be there at 3 hours, and so forth and so forth. Right? So this is the scenario. So now how are we going to make an equation? So let's introduce some variables here. So I'll let H equal the amount, the number of hours, and the mass, let's just let that be M. So what's going to happen is we're going to have M equals 200, the initial. And in this case, what is this bracket here going to be? Remember in previous problems, what that bracket was the amount that we continued to multiply whatever mass we had. We'd multiply it by that bracket to get the new mass. So if something was doubling, for example, we'd be multiplying it by 2. Or if it was tripling, we'd be multiplying it by 3. And then those values, if it was doubling, that's what the bracket would be. Or if it was tripling, that's what the bracket would be. Or if we were dealing with a half-life problem, right? If it was decaying, in this case, this is a decaying problem because notice that the mass is going down. So it's not like a double or tripling program where the mass is going up, where this the amount of this drug is growing, right? It's decaying in the bloodstream, so it's going down. And usually the most popular type of decaying problem that we've been dealing with is half-life problems. So instead of 1/4 of something being used, we'd be told that 1/2 of something would be used, right? And so what we would be doing is we continue to multiply by a half, so then this here, that bracket, would be a half. So the question is, in this particular scenario, what is this bracket here going to be? Now, initially, you might think, oh, 1/4 of a certain drug is used. And so initially, your impulse might be to put 1/4 over here and then have an exponent over here. So it's every hour. So it'd be like h over 1. So we could just put h over here. But notice that this here, it would actually be the incorrect equation, because if we actually test it, how much of the drug, what's the mass of the drug after 1 hour? Well, 1/4 to the power of 1 is 1/4 times 200. 200 times 1/4 would give us 50. But the mass after 1 hour, as we intuitively went through it, is supposed to be 150, not 50. Okay, this here is the amount used, but it's not the amount remaining. So the question is, what did we have to multiply the 200 by to get to 150? And the way you can do that, you can figure that out. You could just take the 150 and divide it by the 200. And what that would give you is 0.75, or if you want to keep it in fractions, you could divide this by 50, divide that by 50, it would be 3/4. So this here is actually the base of the exponent. Okay, now one thing I want to mention is with half-life problems, the reason why, let's say it said 1/2 of a certain drug is used every hour, the reason why this bracket would still be a half is because if you notice, if we start at 1 and then a half is being used, so if we start at a whole and then a half is being used, what's the amount remaining? Well, it's still 1/2. And so this number and this number are the same. And what goes in the bracket is not the amount that's being used, but the amount that's remaining. And so when we were dealing with half-lives, the 1/2 that would go in the bracket, it wouldn't be for the amount that was being used, it was for the amount that was remaining. And because these were the same anyway, you might have thought that the bracket was because of the amount used, but it was for the amount remaining. So in this case, what's happening is if we have a whole and then 1/4 is being used, what is the amount remaining? It's 3/4. Right? So it's not this that's going into the bracket, it's this that's going into the bracket. That's going to serve as the base of that exponent. And then we're going to have to the power of h, like that. Right? And then you could test it. So if you plug in 0, 3/4 to the power of 0 is just 1 times 200 would give us 200. That's the initial mass. If we plug in 1 for h, 3/4 to the power of 1 would be 3/4 times 200 would give us 150. What if we plug in 2? If we plug in 2 over here, 3/4 to the power 2 would give us, what, 9/16? Right? Or you can get the decimal as well. You could take 0.75 to the power 2. I'm not sure what the decimal would be. This is what the fraction would be, and then 9/16 times 200 would give us this 112.5. So what we're doing all the time here is we're actually multiplying, in this scenario, we're multiplying by 3/4. We're multiplying by 3/4. Right? Because 1/4 is being used, so that means 3/4 is the amount remaining every time of the previous amount. So this number, we'd multiply by 3/4 to get the next one. Then 3/4 the next one, etc., etc. You wouldn't be multiplying by 1/4 for the mass that is remaining. Right? The 1/4 represents the amount that is being used. So for example, if maybe they said instead of 1/4, 1/3 would be being used, then this would be 1/3. What would be the amount remaining every time? 1 whole minus 1/3, 2/3 would be remaining. So then 2/3 would serve as the base of that exponent. All right, so kind of tricky to understand. Hopefully you understood that explanation. You may have to rewind it and watch it again. It's kind of tough to explain. It's just in this case, it is still an exponential problem, right? The equation that we end up having ends up being an exponential equation. It's just coming up with this base in this case is a little bit more tricky because you have to really read it carefully. And as I mentioned in previous videos, what I recommend doing is making a table of values, reading it carefully, getting these amounts, and then from the table of values, you can see how you can create an equation. All right, basically the base here for any table of values you make, whether something's growing or whether something's decaying, like in this case, this base here, it's always going to be the amount that you're multiplying to get to the next amount. And you can always get that by taking, to figure out what do we have to multiply the 200 to get the 150, well, we could just divide by both sides by 200 to get that x value, which would be 3/4, right? If something's doubling, like let's say it goes from 200 to 400, we could take 400 divided by 200, take the bottom minus the, or take the bottom divided by the top to get that base of 2. Right? That's how you can always get the base. This is always the initial amount over here. And then the exponent, it's always going to be, if you let the exponent be hours or the time, it's always going to be the time over whatever that period of time to get this amount is given. So here we're told 1/4 of a certain drug is used every hour. So over here, every hour, every 1 hour, it's like over 1. So h over 1 is just h. That's why we have the h by itself. But let's say it was every 2 hours. Then this over here, this exponent would be h over 2, like that. If this was like 2, 4, 6, if this was going up by 2 hours, right? Or if it was going up by 3 hours, if it was said every 3 hours 1/4 is used, then it'd be h over 3 over here. But because it said it's every hour, it's just h over 1. That's why we have that h by itself. But we've gone through previous word problems where this exponent had to be adjusted in a certain way, right, in order for the inputs from the time column to give you the output of the mass or the amount column. Okay, but in this case, because it's every hour, the h is just by itself in the exponent. So this here ends up being the equation for this particular problem. Now in part B, what they're asking for is how long is it going to take for this initial dose to be less than 10% of its original mass. So its original mass is, so the original or the initial mass is 200 milligrams. Well, what is 10% of 200 milligrams, or 10% of that initial mass? Well, what we would do is we would take 0.1, multiply it by the 200, which would give us 20. Right? So 20 milligrams is 10% of 200 milligrams of that initial mass. And so what they're asking for is how long is it going to take this column to get to 20, or it said even less than 20. So how long is it going to take? How many hours is it going to take if we continue this pattern until we get to a number that is less than 20? Now, there's different ways to do this. So you can do it algebraically. You can also do it with trial and error. Now, algebraically, the way that you do it, the method, it's actually a method that's more used in grade 12. I'm going to show you that method as well in a sec. but most likely your teacher's gonna want you to do trial and error. And so what you can do is you can just keep plugging in a couple of h values. And what you would notice is if you continue to plug in h values into this equation, so you go 3, 4, 5, etc., what you would come to is at about 8 hours, if you plug in 8 over here, 3 over 4 to the power 8, you get that value, then multiply by 200, you'd get approximately 20.02 milligrams. And then the next hour is the 9 hours. So if you plug in 9 over here, 3 over 4 to the power 9, get that value, get that decimal. You could even take 0.75 to the power 9, get the decimal, multiply by 200. You'd get approximately 15.02. So notice that at the 8-hour mark, it's just very close to that 10% amount of 20 milligrams. So the answer to part B is it takes approximately 8 to 9 hours. That's why there was an approximately there, because they probably just want you to do it with trial and error. Just continue to plug in a bunch of numbers until you get to less than that 10%, less than and 10% of the initial dose of 20, or the initial dose of 200 is 20, right? So it's approximately 8 to 9 hours, between 8 and 9 hours, where they'll be crossing that 20 milligram mark, right? So that's the answer to part B. Now, if you were to do it algebraically, your teacher may or may not go over this. This is a grade 12 technique to use, but I'm going to show it to you anyway. Just in general, let me show you this rule. It's a pretty cool one. So let's say that we have something to the power of x, and that's equal to b. What we can do is, if we're solving for this exponent, and notice that we are solving for an exponent in this case, right? If you have something in this kind of format, where you have a base to an exponent is equal to something here, let's say b. These could be numbers, these could be expressions, whatever. Let's say that we want to isolate for this x value over here. What we can do is we can use the logarithmic function if you're using a scientific calculator. So what we could do is we could take the logarithm of b divided by the logarithm of a, like that. And I'm not going to go into details into what this means, what a logarithmic function is. This is just something you're going to have to memorize. Again, your teacher may or may not go over this. Most probably won't. This is, again, more so a grade 12 technique, but it's just a cool thing to remember. So for example, like let's say we had 3 to the power of x is equal to 9, right? Because 9 can be rewritten smoothly as a base of 3, we could tell that x is just going to be 2. But what if we had like 3 to the power of x is equal to 5, like that, right? We can't rewrite that 5 as 3 to the power of something, right? So this x value is going to be some kind of decimal. So instead of doing just a bunch of trial and error, you can get that x value right away by doing log 5 over log 3. Right, so it's a cool way to solve for exponents if that's the variable that you're solving for. And in this case, it is going to be the variable you're solving for, right? Because notice that this is the equation, and then the unknown is this h value. So the way we could solve for it is, first off, notice there's this 200 in front. What we want, in order to use this, we need just the base to an exponent is equal to something here. There can't be anything in front of that exponent. So what we have to do is we have to actually divide both sides first by 200 to get rid of that 200. 20 divided by 200 will give us 0.1. And then let's actually change the 3 over 4 to a decimal just to keep it consistent with the left side here. And now notice that this is in this format. right? The 0.75, the base, is like this a value. The x is like the h that we're solving for. And then the 0.1 is like this b over here. And so the h, that exponent would be log 0.1 over log 0.75. And when you do that calculation, I think you'd get approximately like 8.003. So what we got before when we just did it manually, something just very close to 8. So between 8 and 9 hours, closer to 8 hours. That's when the dose is going to pass that 20 milligram mark, or it's going to pass 10% of the original dose, right? If your teacher didn't go over this, don't get too intimidated by this. You could even just skip this part if they just want you to do it manually, but thought I would just introduce this. It's just a cool trick. If you ever get something like this and maybe you're on a test, you're kind of stuck for time and you want to just know what the actual answer is for this, you can just use this formula and it'll always give you what that exact value is. So then when you're doing your trial and error, if you just do this quickly over here, you don't have to waste your time in trying 4, 5, 6, etc. You could just go straight to that 8, right? Try that, make sure that it works, then try the 9, make sure that it's less than the 20, and then you can answer the question quicker. All right, so this here, it's the equation, that's part A, and then how long does it take to get to 10%? Approximately 8 hours.